And now let's move to the second speaker. And the second speaker is Professor Tong-Earn Tay. He is professor at the Department of Mechanical Engineering, National University of Singapore. His research interests are in computational modeling and analysis of progressive damage, failure, fracture, impact, integrated design, and manufacturing. Today, his talk is High-Fidelity Computational Failure Analysis of Composite Structures.
Hi, good morning, good afternoon, or good evening. My name is Tay, and it's my pleasure today to share with you some thoughts on high-fidelity computational failure analysis of composite structures. I'd like to thank Professor Lubino for inviting me to do this talk. Firstly, I would like to acknowledge the contribution of my colleagues, Professor Tan, and my postdocs, Jie and Kartik, a PhD student, K.H. Leong, and my ex-postdocs and PhD student, Xing Lu, and also my collaborator, Professor Jun Kayanaji from Tokyo University of Science. I'd like to also acknowledge the support of the A-Star under the grant and the Polymer Matrix Composites program. This is the outline of my talk. First, I will talk a little bit about introduction of various models that currently being used to model progressive damage, smeared crack models, discrete crack models, and then something that we developed called separable cohesive elements. And also adaptivity being incorporated into what we call a discrete smeared crack model, or ADISC, and the reversed ADISC, which is termed coupled failure model. And then I will talk about rationale behind developing adaptive multi-fidelity model, where only physics that is required for the damage progression is being modeled faithfully. And then I'll talk a little bit about the most recent work that my group and colleague, Vincent, is working on multiscale modeling with something we call the direct FE squared. And most of the talk here will be benchmarked. The results will be benchmarked with open hole specimens, and then we will conclude with some comments on the future outlook for progressive and multi-fidelity modeling. So if you look at failure in composites and specifically damage and cracking in composites, you find that there are all kinds of things happening, even for a so-called simple specimen like the open hole tension. So in experiments, it is not unusual to see large longitudinal cracks in the 0 degree ply, and then some minus or plus 45 cracks, distributed cracks, and then also very diffused cracking in the 90 degree layer. So you can categorize the damage into various types: distinct micro matrix cracks, diffused micro cracks, which are very closely spaced together, and there's also delaminations, and then finally fiber damage. So modeling these kinds of cracks with multiple fidelity is a big challenge. So in modeling, you can start from a very simple beam-like model to layered shell model or stacked layer model, or in this case, this is usually called a mesoscale or the ply level scale, and then right up to micro scale, which is a fiber matrix modeling. And depending on what you intend to interrogate, you will apply the appropriate models at the appropriate scale. Now, at the mesoscale, you have various options. The most common and probably easiest to implement is what we so-called smeared crack method, and where the damage, which is modeled by the degradation of the stiffness properties of each ply, is smeared over the area that is considered damaged. Now, this is, of course, a gross simplification and is unable to model things like the lamination and large cracks. And then on the other hand, you can appeal to what we call a class of problems called discrete crack methods, and of which XFEM, a phantom node method, an augmented finite element method, and then something that we developed together with Professor Pino from Imperial, called the floating node method. And all what this does is that they want to model the discrete crack explicitly in the laminate. And of course, what this means is that it's very compute intensive if you have just the discrete crack model. This is an example of a smeared crack model applied with the cohesive model for the delaminations. So here what we have is that you have the low velocity impact event in which the delamination is delamination and matrix cracking have been modeled through the impact event. And then after that, you remove the impactor, and then you change the boundary condition to compression, in-plane compression. Now, in this case, you can see that even though the model is primarily smeared crack, you have two different, very different behaviors. On the left, you see that for this particular layup, the dominant failure is global buckling, whereas on the right, for this configuration, you have sublaminate buckling. Now, this is despite the fact of the shortcoming of a lot of the smeared crack modeling, and you can predict this failure mechanism. So the smeared crack model has got its capabilities, although it has its limitations as well. Then this is an example of a discrete crack model. So the floating node method, which has been developed previously, what we do is that we take a regular finite element mesh, and you can, by seeding floating nodes, so-called, you can then put the discrete crack in the model where you your stress analysis predict the failure will occur. So, for example, in a 3D mesh, these 3D elements represented by the blue elements, they will they can be partitioned by these nodes into various shapes, like brick elements or wedge elements. On the other hand, because you have cohesive elements between plies, these can be inserted on the fly, but also that these cohesive elements can be partitioned as well. So this is possible due to the two technologies. One is the floating node method, which is given in this reference, and the other is what we call the separable cohesive elements, which enable you to partition the cohesive elements and model the interaction between two matrix cracks in the adjacent plies. And previously, we have shown that this method, discrete crack modeling, is able to model both the delamination in open hole laminate as well as unnotched laminates, as well as the matrix cracking in both cases. And more recently, we have extended the discrete crack model to model a compression hole, open hole compression failure. So you can see here that this, on the left, the picture depicts the failure of the outer ply, which in this case happens to be a 45-degree ply. And then here you can interrogate the damage at each ply, as well as the laminations between various interfaces. The discrete crack model has also been applied to low velocity impact. So in this case here, we show the classic peanut shape damage pattern that you get when you have low velocity impact of cross-ply laminates here. And we have extended it to quasi-isotropic, but the picture is not being shown here. A problem with discrete crack model, despite its closer fidelity to the physics of fracture, is of course computationally intense and not practical for large structures, because you have to basically model millions and millions of cracks. That's not practical at all. On the other hand, the smeared crack model, although as an efficient representation of numerous micro cracks, suffers from several drawbacks. First is that it is, of course, it may have convergence issues, and then material stiffness softening can cause distortion of elements. Also, generally, they are unable to model interaction with the delamination, between delamination and matrix cracks faithfully. So recently, we've proposed a adaptive discrete adaptive discrete smeared crack model or coupled model. This means that we want to preserve the fidelity of physics where and when it is needed. That is at the active damage sites, and where the damage is not propagating or inactive, then we can leave it as a smeared crack model with a reduced stiffness matrix. So this is possibly less compute intensive, and we published this work, and I would like to show you some results later on. But beyond this, we have now proposed a adaptive multi-fidelity model. In this model, what we do is that instead of modeling laminates through a 3D finite element, we can progressively change the track where the damage occurs, and where it is needed, we preserve the 3D nature of the model. Where it is inactive, we can convert it to shell or plate elements. So the plate or shell elements may be where you start, where there's no damage, or when the damage starts to become inactive, no longer active, then you can convert some of these damaged 3D elements into back into shell elements. So it is shell to 3D and then back to shell. Adaptivity. There are quite a number of issues that we need to consider when we do this. So this is an ongoing work. We haven't finished it yet. So some of the issues for adaptivity from a pure discrete model to coupled model is that we have to ensure the energy consistency in terms of fracture energy and stored energy for the model transition. And also you have to decide on what is a suitable crack spacing as well as a characteristic length. How long is a crack allowed to grow and still be modeled as a discrete crack, or when do you actually make it into a smeared crack? So those are issues which are very pertinent. Recently, an ex-student of mine, Lucing, he proposed a reverse. Instead of starting out with a discrete crack in 3D, he start off with a smeared crack. That means to say when the damage initiates, he uses smeared crack model. And then as the damage grows, he then switched to a coupled smeared and a discrete crack model. That means some of the larger cracks are retained as discrete models as well, but the less active damage are converted or retained as smeared crack. That is also okay. And then my ex-student told me that this is more efficient than what I proposed previously. So we can benchmark this kind of models with open hole tension, for example, for which experimental verification and data is available. So in this case here, the benchmark is to have a pure discrete crack model. So even in this case, we have to make assumptions of how much is there is a crack spacing and so on and so forth. But you can see here that the final damage pattern as far as the matrix cracking is concerned is very similar to experimental results. And you can see that there, in this case, there are more matrix crack, diffuse crack in the -45 ply than the +45 ply. And this is because the -45 ply is in the internal part of the laminate, whereas the +45 is actually the surface ply, where there's not that much diffuse damage. And this model, the discrete crack model, is able to pick that up. And if we have a adaptive discrete smeared, that means to say that we would like to have the parts that are that have many diffuse cracks, they have to be smeared. And so we can do this by smearing the damage in the 90-degree ply, and also in the -45 ply, which is internal. And that seems to work pretty well. And if you have a comparison, and this is a comparison of the benchmark discrete crack and the adaptive discrete smeared crack model on the right. And then we by using this method, we can say we save up to 36% of the degrees of freedom and a CPU time about 22%. However, of course, this is model dependent, and this model is a relatively small coupon size at this point in time. For the reversed A-disk, the important thing here is the graph on the right. Here we see that the pure smeared crack model given by the red squares actually underpredicts the strength. This here is the strength in megapascal when compared to experiment, whereas the discrete and the coupled model, despite being more efficient, is able to predict the strength more accurately. I'd like to talk a little bit about Fe squared. I have not much time to talk about this. Essentially, what this is that my colleague Vincent has proposed a technique called the direct FE square. Now, the FE square method is not new, but the direct FE square is a very good innovation because it enables you to use commercial codes like Abacus with a minimal coding, and also FE square allows for analysis of structures made of heterogeneous material without the need for homogenized material properties. So, which means that at the Gauss points of the elements, you actually interrogate the material, the fiber matrix at the micro scale, so that the implication is that if we know the failure at the micro scale, we can port it up to the meso scale or ply level scale without any need for ply level or homogenized failure criteria. And I think personally that this can be a big deal if it works. However, you can imagine that such a technique is very compute intensive. So, but anyway, we have begun to do some studies, and one of which is to look at the behavior of angle ply laminates with FE square. And in this case, we have comparisons between experiment and the computational model from FE square. So the experiment is taken from this paper, which is given by the dashed lines, and the simulation is given by the discrete triangles as well as the crosses here. And the agreement is pretty good. What this shows is that the larger angles are actually dominated more by the shear, the properties of the shear, and the smaller angles are dominated by fiber behavior. And we are in the process of also measuring the fiber changing angles using this technique. I'd like to show here a little bit of a work that we have done with Jun Koyanagi from Tokyo University of Science. He has taken the FE square, the direct FE square method, and applied it to this case of a composite ring with a fiber in the axial direction and undergoing impact through a split Hopkinson par. So this is the finite element model, and he applied the FE square method to the ring at the part where it breaks. So you can imagine as soon as this is undergoing a horizontal impact, this ring will break here. And this is what June shows. At the micro scale, you can have a failure criteria which you can apply. At the micro scale and at the Gauss points, you have these failure explicitly modeled at the micro scale. So this is on the left. This is the FE mesh of the micro scale at the Gauss points, which June used. So this is being used with permission from Professor Koyanagi. I'd like to end the presentation by saying a few words about the techniques for modeling progressive damage through multiple scales. So as you can see, we now have tools to deal with damage and progressive failure at various scales. At the micro scale, which is a fiber and matrix scale, you can have concurrent FE square or direct FE square to deal with this. But however, this kind of technique is impractical for structures. And then at the meso scale, which is a ply level or the ply level, small coupon level, you can use discrete crack methods or the smeared crack methods. But for a larger component scale, this again, discrete crack methods, it's not very practical. What we've done is that we have coupled some of these methods. So these discrete crack methods can be coupled with the direct Fe square at the micro scale. And then the discrete crack methods can also be coupled with the smeared crack methods at the meso scale or higher, so that we can have a hope to model progressive failure at the larger structures. That is the future trend. We hope that we are able to model progressive larger structures with a greater fidelity to the physics. And then also, if we can get more fundamental properties from the lower scale, from fiber properties and matrix properties, then we can see that we can perhaps be able to model failure at the larger scales with these more fundamental properties. So I like to end my presentation with some publications here, which I have listed for your information. For those of you who are interested to find out more, you're welcome to contact me. Thank you very much for your kind attention.
Thank you very much, Professor Tay, for this informative talk. Here's a question. So from the attendees, he said, "A nice presentation, Professor Tay. What's your thoughts on phase field continuum damage methods? They are mesh insensitive due to regularization."
Yeah, that's a good question. We have not really done much work on that, but I have ex-students who are working on that, and I believe there are probably advantages to dealing with it. And also, we are working with some professor from China, Shanghai University on that field. Yeah, but I don't have many results to show at this point in time.
Okay, thank you. And next, Professor Giolupino, please, you can unmute and ask a question.
Thank you very much, Steve, for a very nice presentation.
Thank you.
I have a question about your feeling about integration of computational technologies. What I mean, you know, now we have plenty of approaches ranging from smear models, damage mechanics, micromechanics, the discrete mechanics, phase field. And I feel that at the end of the day, when you come to engineering, it's difficult to have an automatic, a kind of tool that is going to optimize and automatically select and substructure the computational domains to apply the different techniques. And what is your feeling about this? What is the path to go to make sure that all these things together become a kind of engineering tools, merging everything?
Yeah, I think the key here is two keys here. Firstly is that computational power and fidelity to physics. So damage and progressive damage in particular, I believe, is that not all parts of the structure is active at any one time. So I think as a computational efficiency and power increases, we should be able to use adaptivity to understand the physics and then track the damage. And I think the other approach that some other researchers are adopting is to simplify and take out some of the pertinent or the relevant physics, and then try to simplify what's going on in the fracture process. So that may work, but it is not a general approach. So that is probably quite problem specific. Yeah. But both approaches is probably a good way to go forward.
Thank you, T.
Thank you.
Thank you. And last question from Professor Senjo, please.
Thank you very much, Professor Tay. It was a very nice talk. And I think my question is partially answered from the previous question. But again, the adhesive nature, how the adhesive strength between the matrix and the fiber will be a very important component. Yeah. And how do you generalize your model that it can be applicable to all? Because, for example, if we go to the thermoplastics as a matrix, it will be very different ball of game, because they have a very different failure mechanism over there.
Yeah, absolutely. I think a lot of this work is done at this point in time. We're using thermoset composites. And then if you go down to the lower scale, Fe square, that's what we think. Fe square has got some potential because it directly ports the information from the microfiber matrix scale to the meso scale. Now, of course, we don't really know a lot of things happening at the micro scale, characterization, as you mentioned rightly, the interface properties between the fiber and the matrix. And so for a long time, we have been, coming up with a lot of empirical or semi-empirical failure criteria at the mesoscale or ply level. So going into the micro scale, perhaps we then have a chance to actually interrogate and see what kind of parameters we need at the micro scale that can be directly influencing the structure at the ply and the laminate scale. So this is one fundamental work that we hope this technique can achieve, at least for coupon level type of work. Thank you for your question. It's a very important question.
Thank you.
Thank you again for Professor Tay.